attain a certain state equals the entropy. So the more of those ways, the greater the entropy. So in a way, when a system has a lot of freedom to move within the state and change the configurations while maintaining the same energetic configuration, you can say that the system has a high entropy. As opposite to that, you have the enthalpic term, which is you can think of that as energy stored in chemical bonds. So so in a way, in order to have a spontaneous process, the free energy term has to be lower than 0. How do you attain that? You have the enthalpic gain when the atoms come closer together. So in a way, love of a kind, right, brings that gain. And you talk about the entropy, which is a negative term, right? So you have a cost because the energy gets basically higher as the entropy is lowered, right? This is what you have from that equation. So in a way, you have to balance these two things. So the enthalpic term has to overweigh the entropic term. So eventually, the atoms reach this particular state here. They're somewhere in the middle. The two types of forces are being balanced. The attractive forces, which are van der Waals forces, coming from the dipoles and the direction of the dipoles. These are the attractive forces. And you have the repulsive forces, which are electrostatic forces. So eventually, the atoms settle in one of these states, and they're basically fluctuating. They're vibrating between something like here, between pairs of states. So let's go next. So this is just a little bit more detailed elaboration. So what happens? So you have two different types of materials. Of course, that's a very rough categorization, but I think it's useful for you to know. So you have monocrystals, so things that are made of single crystal. So think of this brick here, and think that this whole brick, regardless of how big or small it is composed of a single crystal. So that crystal is uninterrupted, and it's just covering the entire volume of this brick. This brick, for our purpose of our discussion here, you can consider as a material. And you have different types of materials that are polycrystalline in nature. So they are composed of multiple crystals. So all these yellow lines are actually the boundaries between individual crystals. So when you talk about a nanomaterial, you talk about a material like this. So a material in which a big chunk of the material is composed of very small crystallites. Okay. So that is the fundamental difference between a bulk material, something like this, monocrystalline, or something that has really, really big crystalline grains in the micrometer domain, and something that has smaller ones. Now, the trick or the question that you may want to ask me is, how do you make this, and how do you avoid making this? So what is the trick? So there's a couple of chemical principles that people use when they are making nanomaterials, and this is one of them. One of them is actually it's listed here. You can see that it's a little bit complex. Not really complex graph, but you have like 3 curves. So what you can see that you have 3 lines, and they are all plotted as a function of a term that is called supersaturation. So that term is very, very essential when it comes to making of nanocrystals. So you'll see why. So as you increase supersaturation here, you have an increase in the nucleation rate. So when you have a very high supersaturation, nucleation rate is high, and you're going to get bigger or smaller crystals. What do you think? Smaller actually. So, and you're going to see why. At this point, we haven't really tackled that yet, but very soon you'll see why. So you have crystal size rate dropping as a function of the supersaturation. The nucleation rate is increasing, and the growth rate is also increasing as the supersaturation is increased. Now, so it might become clear after we cover this. So these are a couple of basic chemical equations. There's nothing really complex here. But so let's cover them one by one. So the first equation is just describing the transition of atoms in a liquid state or it could be in a gaseous state as well, into solids. So you have, I picked one compound that's calcium sulfate. We could have picked any other compound. So S stands for the fact that this is a solid compound, okay? And you have calcium ions, and AQ stands for the fact that they are in the solution, they are in the aqueous state. So you have calcium ions and sulfate ions, and they're, you know, swimming in a solution, such as this water. And so how do you initiate the precipitation of these ions into nanocrystalline material? That is the question. You do that by increasing the supersaturation. So you keep on increasing the concentration of these ions up to the point where you reach a saturation. And saturation is very, very, you know, defined concentration. Anything above that concentration leads to supersaturation of the solution. Now, the greater the supersaturation, the greater the chance that your solution will precipitate these nanoparticles. So how do you describe? So in this state, when you have a precipitate forming and you have, you know, ions in equilibrium with a precipitate, you have this particular equilibrium constant, and you have the concentrations. These are the values within the brackets. And so basically this is taken as one, as unity, because it's a solid state. And so you end up with just the concentration of these two ions in the solution. And so when they are in equilibrium with the precipitate, that concentration is known as solubility product. So it's telling you actually how much ions you have in the solution that is equilibrated with the precipitate. And S is the supersaturation. So we arrived at that crucial parameter. So what is Q? Q is actually the concentration of these ions in any solution, in any state. And KSP is the solubility product. So it's a very defined quantity, okay? So it's a constant. So if you want to know what the supersaturation of your solution is, you need to know the concentration of the ions. That's going to give you the value of Q. So think of this, Q is the same as here. It's just that this is a concentration in your solution, whatever it is. Now, so supersaturation can have, right, values that are lower than 1, which means that the solution would be undersaturated. You won't have any precipitate forming under those conditions, or it can be above 1. So typically, if it's just slightly above 1, you still don't see any precipitation, because the solution can exist in a metastable state for very long periods of time. But if you exceed that critical supersaturation, if you go really high, say like 10 to certain number, you're going to get a precipitate. So that's what chemists call crashing. Our solution crashed, which means our solution, the ions started forming crystals, and these crystals fall down typically and into the bottom of the solution as precipitate. So in energetic terms, this is one of the most important graphs you would see in the theory of crystal growth. It's relating the free energy of the crystalline particle forming in a solution. So you see that in total, the free energy goes up and then falls down. As it goes up, this process is not energetically favorable because it goes into the positive value. It has to go into the negative range in order for the process to become spontaneous. So, and this NC that you see here is the critical size of the nucleus. So everything below the size here, NC, means that these little embryonic crystals are forming in the solution, but they're also dissipating. And they're forming and dissipating, all until they form the size that is larger than this critical size. So once they cross this barrier, they start to grow spontaneously. So you're going to have individual atoms from the solution getting attached to these crystals, and they're getting bigger and bigger, and they're stable. They can't go back anymore to the solution. They can't dissolve. So this entire curve is actually composite of two terms. So one of them is the volume term. This is the volume term, and this is the surface term. So when you break down this free energy to two terms, so the volume term is always favorable, right? Because essentially the crystal, the atoms inside the crystal favor the crystal formation. But the surface term is not favorable because the surface is not really, there's an interfacial energy, there's the entropic cost that comes with the formation of this interface. So that process is never actually favorable. But when you combine the volume and the surface, you realize, right, when the particle is very small, the surface is dominant. Because it's very small, the surface is very big compared to the volume. But when it grows, you know, the volume is big and the surface is proportionally smaller. So, yes?
Why not the critical size is at when delta G is 0?
Why is not 0?
NC, when the delta G is 0, why is that size not called critical size, NC?
When delta G is 0, because everything after the maximum is actually when the crystal starts growing spontaneously. Yes, so that is the, you know, this is kind of the energetically, you know, favorable, because at this point, think of that, after you cross the hump, the surface becomes less important than the volume. So that is kind of, but it's a good question. It's a good question because, you know, you might wonder, these are the little details that come with the theory. So yeah. So another thing is that what you see on the right graph, this is also one that I really like a lot. So it's telling you a difference between two ways of nucleation. So by nucleation, I mean the formation of these primary crystals in a solution. Okay. So there are two ways these nuclei can form. They can form in the solution, like inside this water, let's say. Like that is called homogeneous nucleation. But they can also form on a foreign surface. So that surface can be the wall of this bottle. But it can also be a dust particle that is, you know, an impurity inside of this water. So nothing is pure, right? You can't prepare 100% pure solution ever. You're always going to have some impurities, be it, you know, foreign particles or bubbles, or, you know, some kind of, you know, background cosmic radiation, you know, which is, you know, very, very ultra fine effect, but still existent. And another thing is that you always have the vessel, the container walls present. And believe it or not, but right now the theorists in chemistry haven't figured out whether actually homogeneous nucleation ever occurs. There are theorists who claim that it does, and there are theorists who claim actually that every nucleation always is heterogeneous. So how can you test that? How can you make a solution that is actually not touching any container? Can you make it? Well, you can make it under one conditions.
Keep on evolving.
Keep doing what?
Evolving. Let's keep it in motion.
Oh, keeping it in motion. Yeah, or steering. Still, you will always have, you know, the entire bulk of the solution will be in contact with some container.
So
Yeah.
we can use the super hydrophobic surfaces in which we can put our solution, so it won't touch the surface itself.
Well, you will still get something, right? Still something would touch the surface. Because something has to hold the solution, you know, so that's going to be something. So there is one way, there's vacuum, right? Yeah, if you have a solution in the vacuum, right, then it's really nothing. But what is the problem in a vacuum? What's going to happen with your solution in vacuum? Right, it's going to evaporate. But yeah, it's just going to dissipate. You know, so you can't really have a. So that's an experiment that's actually, you know, one of those you know, experiments that are impossible to test. So, but this graph is actually showing you. So this, what you see here is the chemical potential divided by KT, which is also a way of phrasing supersaturation. So as this supersaturation is increasing, you have two curves. So HEN stands for heterogeneous nucleation, and HON stands for homogeneous. And if you go all the way, look down, you'll see which one starts first. Heterogeneous. So actually, if you want to have a controlled growth on a surface, such as you want to make a film and not particles, you want to increase this supersaturation very slowly. Like you want to add your ions to the solution very, very slowly until you hit this range where you're going to have a very controlled surface process. Otherwise, if you do it very fast, you're going to get a, you know, homogeneous one, because it's going to be more favored at higher values of supersaturation. So when you want to make nanoparticles, What do you think you need? Do you need low values of supersaturation or high values of supersaturation?
High.
Very high, yes, exactly, very high, because you want to get, you know, precipitation inside of the solution. You want to avoid the surface growth, and you also want to have as largest density of nuclei as possible. And this is what the next graph is showing you. So the nucleation rate is directly proportional to supersaturation. So if you increase the supersaturation, the nucleation rate goes high. So when you have a large number of nuclei, you're going to have smaller particles, right? And the making of the nanomaterials is all about avoiding the extensive growth of the particles. So you want to minimize their growth. You want to make them as small as possible. So so that is, you know, that is one of the tricks. If I had to put it in like even simpler terms, that would mean that if you have two solutions and you're mixing them to produce a precipitation reaction, it means you have to mix them as abruptly as possible, right? So that is the trick. If you want to make nanoparticles, you know, you have to have a very high nucleation rate. How are you going to get that? You're going to get it by having a very high supersaturation. And how are you going to get that? By mixing the reactants at very high concentrations as abruptly as possible. So in contrast, if you want to have a monocrystalline material, a complete opposite of nanomaterial, you want to do everything opposite. You want to have a very low nucleation rate, because you want to have, ideally, in a whole solution, you want to make one nucleus. And that nucleus is going to attract all the crystals, and they're going to go into one crystal, right? You often see that with these crystal growth experiments, when they put the crystal inside of the solution, and they usually have extremely low supersaturation ratio, because they want to have that crystal growing. You know, they don't want to have particles forming in the solution outside of the crystal, kind of randomly precipitated. So, so this is also basically telling the same thing, the same story. As you increase the supersaturation, you go from bottom to top. The number of atoms in a particle is, you know, getting lower. So in a way, the particles are smaller, right? So supersaturation, in a way, is the first and the most essential parameter that chemists use in making nanoparticles. That's the first trick. You know, all the other tricks come next, and you know, they involve, you know, the control of the interparticle potential, such as, you know, zeta potential, the pH values, and they're definitely far less intuitive. You know, it's really a qualitative game. You know, there's no model that's going to tell you, you know, exactly, you know, what to add, how much of things to add, what kind of chemistry to run. So it's, you know, it's really a trial and error game, and I'm going to mention more about that later. So so again, the higher the supersaturation, we are repeating this, the lesser the crystallite size. And if you go to geology, you see the same effect. You know, if you have two types of rocks, so the basalt rock is formed in volcanic eruptions, right? So you have lava emerging to the surface, and it's cooling rapidly. So you have a very, very actually, you know, high supersaturation involved there. And the process is very rapid, and you form very small crystals. And you can see that these crystals are super tiny. You can even see these little speckles. And you compare it with granite, and you can even see that these are much bigger, right? Of course, the effect would be much greater if we were to magnify this under the microscope. So granite forms, you know, it's in a much slower process. It's like a slow cooling process. So geology is always, you know, a good way to look at the crystal growth phenomena. Another thing is that nucleation rate is inversely proportional to the interfacial tension. So interfacial tension is another one of those parameters which are extremely difficult to control. It is extremely difficult to control because it's highly chemistry dependent. So it's going to, when I say chemistry dependent, I know it sounds a little bit vague. What I mean by that is I mean that it's dependent on the chemical composition of whatever you're growing. So if you're growing these calcium sulfate crystals, you know, it's really difficult to change it interfacial energy, because it's just going to be, you know, kind of dependent on the compound that you are growing. So calcium sulfate is going to have one interfacial energy, calcium phosphate is going to have another, calcium sulfide is going to have the third one. So, but this is the effect, general effect. If you have basically a lower surface energy, the J would be the crystal growth rate. This is a typical way of denoting that. It's going to grow faster. Okay. So why? It's kind of like a surface tension effect. You know what surface tension is in liquids. If you put the water, as a droplet on a surface, it might retain the spherical shape because water has a comparatively large surface tension, and because there's this pool of the water molecules towards the inside of the droplet. You have a droplet, and all these molecules are pulling inside. So you have the same effect in crystalline materials. If you have a particle, could be spherical, you also have this pool of the atoms on the surface inside. Why? Because think of that. The atoms inside a particle have their neighbors. So their coordination, they're kind of like all the bonds are satisfied. But those at their surface do not have their neighbors. So they are seeking more neighbors and they are pulling inside, right? So in a way, when you have a high surface tension, all these atoms are on the surface are busy reaching out inside, and are not really free to interact with whatever is coming on the outside. And that is the crystal growth. The atoms come from the outside, and the surface has to be available for bonding. So that is another, and this is just the reiteration of what I mentioned, that the nucleation rate for heterogeneous nucleation is typically higher than for the homogeneous. So so that is an effect that it's really unavoidable. And there's a joke that says that good chemists are recognized by the amount of impurities that they bring to the lab with their beard. So so very often the addition of these foreign compounds, foreign impurities, is essential, and you cannot actually run a synthesis process without the right impurities. Believe it or not, but we had cases of whole companies going bankrupt because of the effect of impurities. There was a company and they were synthesizing a drug, and the synthesis process was so highly dependent on a particular foreign impurity that it worked for the time being that that impurity was present, and it was actually undefined. It could have come from their distilled water or from a particular salt. Nothing is ever pure, right? Everything comes with some impurity. And then at one point that impurity disappeared and they couldn't repeat. They couldn't synthesize the drug anymore. Actually, they were getting the drug, but it was a different optical conformation of the molecule. And it did not actually have the same biological effect. So, and the company lost, millions of dollars. So I mean, these subtle effects are extremely important in the synthesis. And so these are some of the methods. Some of the methods that are typically used for the synthesis of nanostructured materials. And we're going to start with the precipitation. We're going to start with the precipitation because this is the first method that I always choose in the lab. Okay, so when we need to synthesize a material, my first question is, can we precipitate that? And if we cannot precipitate that, then we try some of the alternate methods. And I'm going to tell you a couple of reasons why I think that precipitation is a very good method. So there are different ways. There are different types of precipitation. I listed a couple of them. There's a simple abrupt precipitation where you kind of just mix the chemicals. You have one solution and another solution. You pour one into the other, and that's it. Extremely simple. Can't be simpler than that. And then you have layer by layer growth, which is something more complex, where you have a surface. It's kind of like more controlled surface growth. Then you have microemulsion assisted. I'm going to mention that as well, and solid gel. But let's go slowly. This is another thing that I want to tell you. So before we proceed to mentioning and elaborating these methods in more detail, so I showed this graph earlier, and it's a good answer to the question you might have: why do we need to pick the right synthesis method? Because the properties of materials, especially nanomaterials, are going to be strikingly dependent on the method of synthesis. Again, these are indium particles, and they were made by two different methods. One of them is ball milled, which is the mechanochemistry method, and the other one is melt spun. So, their melting point dependence on the particle size is completely different depending on the method. So you know, how you choose the method can actually have, you know, really strong effect on the properties. And also another fact is that you cannot synthesize everything with everything. So what I always give to the students is I give them a list on the exam. I give them a list of 10 materials on the left side and 10 methods on the other, and they have to link them, right? I think it's a good exercise because, you know, there's always an ideal method for every particular type of material you want to make. And there's also methods that you can never use. You know, they will never work. And this is one case. So let's assume you want to make collagen. Collagen is the, you know, the most prominent protein in our bodies. So it's the essential protein of the connective tissues. And so let's assume you want to create, you know, you want to use electrospinning. How does electrospinning work? You're basically, you know, injecting a compound through a needle, and that needle is attracted by the electric field, so it goes out of the needle in threads. It works well for what types of materials, do you think? Polymers, yes. For very soft materials, for polymers, and collagen is a you know, protein. It's a polymer of a kind. But it doesn't work for ceramics, right? For ceramics or for metals. It's not going to work because you need something that's viscous, that's flowing, right? So you can create wonderful electrospun collagen, but if you do that with collagen and you add ceramic component, which is hydroxyapatite in this case, you're going to end up with this, you know, very ugly looking material. So, you know, so this doesn't work. Another example is annealing. Annealing means bringing something to high temperature, kind of like heating in a way. So, so you cannot heat. This is quite the opposite, right? Can you heat collagen? You cannot. It's just going to denature, break apart. Can you heat polymers? Not really, you know. So it works well for inorganic particles. You have ceria, zirconium oxide, and silicon oxide. You can create these beautiful particles with annealing, right? And you have, you know, this is the edge of the particles. But if you do that with polymer, in this case, this is polylactic acid, you're going to get some, you know, mushy pattern that's actually, you know, not really a pretty material at all. So for nanoparticles, one of the things you want to avoid is aggregation of the particles, right? So and that's the biggest fear of everyone working in this field. You create these nanoparticles, but what if they aggregate and they form something like this, right? They form this continuous network, and they are no longer nano, right? You need to have a discrete nature of these particles. And in this case, you have this bar is 20 nanometers. See, so these particles are probably around, you know, 60 to 80 nanometers, and you see they're discrete. You know, every particle is, you know, separated from the others, and you can call this type of material a nanomaterial. This you cannot.
Those dots.
These atoms here, these dots. These here. That's EDS pattern, as she noticed. So that's basically the diffraction of electrons. So that's a diffraction pattern, and I'm going to mention that. We're going to cover diffraction. So this is typically coupled to TM. These are transmission electron microscopy images. So precipitation. These are some of the properties of precipitation, and they are the reasons why I like this method. So it's simple. One thing, you know, you can turn your kitchen into a lab, you know, in a way. It's cheap usually, so you avoid, you know, expensive, complex setups. So that's another reason. So one of the, you know, it really depends what you want to have. But another property, sometimes not so desired, is that it's you know, low crystallinity and low internal ordering. So you can get amorphous materials very easily. So when we talk about crystallinity, it means basically the degree of crystalline order. So every crystalline pattern, we don't have time to cover that, but it's kind of like a crystal lattice, and it can be perfect, but you can always have these twisted bond angles, change distances between these atoms. In those cases, the crystallinity is a little bit disrupted. And if this is completely disrupted and you no longer have any long-range ordering, then your material is amorphous. It's no longer crystalline. So typically it's liquid to solid. This is how usually it works. You have a liquid and you have your ions of one type dissolved here, and then you add another reactant into the solution. And so the mixing of the two solutions creates a precipitation reaction. It's supersaturation controlled, so that's one of the good things. And it is very sensitive to the addition of additives. So the additives typically absorb onto the particles, and they can control the crystal growth. So these could be proteins, these could be sugar molecules, these could be soap molecules. So these are the typical choices. And so they're typically performed at room temperature. And this is one of the coolest things. You can really control the morphology of the particles really easily by controlling the supersaturation again, or the presence of additives, or the rate of addition of reactants, like how quickly you increase the supersaturation. Usually, if you slowly increase the supersaturation, you end up with particles like this, like planar particles, or uniaxially grown, like needle-shaped particles. These are also some kind of plate-shaped particles. They're like growing along like 2 dimensions. And if you have very high and very quick containment of the supersaturation, you get something like this. You get very small spherical nanoparticles. So in a way, that's one of the good things. Now this is maybe going. I don't even know when this is printed out. Can you read this? You can read. Okay, so that was my worry, that actually it's not going to be, that the letters will be too small. So this is a little bit more advanced, right? And I said a lot of good things about the supersaturation concept, but there's a lot of weaknesses, right? And you should always remember that there are those, and there's no perfect approach in anything really. And so these are some of the problems. So you usually, I don't know if you might be aware of that chemists in particular divide effects, physical-chemical effects, to thermodynamic and kinetic, right? So thermodynamic is something that is really driven by the free energy. You can if you know the free energy of the process, you can calculate. You can know if the free energy is dropping, it's spontaneous. If it's increasing, it's not spontaneous. So, but there are kinetic effects which come from the presence of some additives that are going to change that kinetic route, which goes from the reactants to the product. Okay, so supersaturation is extremely sensitive to those effects. So supersaturation itself is a thermodynamic concept because it's related to free energy, as we've seen earlier. But when you put that equation, it doesn't tell you about the kinetic effects. It doesn't tell you about hey, we have these ions in the solution, and these ions are going to actually be attracted to the surface of this particular plane of the particle, and they're going to affect the process by blocking these ions and so forth. So these effects are not going to be told you by the concept of supersaturation. So typically when you use supersaturation, you calculate the ionic concentrations, right? But you don't account for the fact that some of these ions are not available, right? You think they are available, but some of them might form complexes. And so in that sense, you always have a reduced concentration. So there's a lot of other effects, and I don't know how much time we have to cover all of them, but this is definitely a good, good source for you to read about them and maybe explore more. So let me see which one would be really interesting. So another thing is that So very often when you look at a supersaturation concept, you know, and people, when they report methods, they rarely ever tell you. They say we mixed, you know, the solution of you know, calcium chloride and the solution of ammonium sulfate to get calcium sulfate, but they don't tell you which solution they added to which solution, right? And actually, when you think about that, right, if you add, you know, so if this is a solution A and this is a solution B, and you keep on adding, you know, these ions from the solution A, they're going to be in much lesser concentration around these nuclei as they form. So in a way, so that's one thing, and that's actually the extension of the fact that you never have a uniform distribution of supersaturation throughout the solution. So think of it as you're adding this little droplet, and it's falling here, and it's forming the precipitate here. So you have these local areas where actually supersaturation is high, and that is where this droplet is mixing with the solution, and that's where you get a precipitation process, right? So so like, how can you account for that gradient of supersaturation? Can you? You know, these are all things that are really, really, you know, impossible to tackle. And so this is what I tell you basically. You know, so the highest supersaturation will be along the edge of that droplet. So so in a way, I think this is a good you know, introduction to the statement, to actually something I want to tell you, and that is that you know, back in the 1940s, the last attempts were made to create a theoretical framework which would help chemists and physical chemists actually predict, using theory, the materials that they would make. So in a way, people had this idea that, okay, we're going to build this theory, and we're going to have this, you know, computer, and we're going to input the properties that we want to have in our materials, such as the particle size. We want to have, you know, this type of crystallinity, this type of particle shape, and the computer is gonna, the output would be the properties. The computer is gonna say, okay, you need these concentrations, and you need to add them at this rate, and so forth. And so all these attempts were actually driven by industry. You know, a lot of industry at that time. It was particularly in Russia and in Western Europe, in the Netherlands. So some of the notable attempts. And then what happened? These attempts failed. Okay, so they failed, and now, you know, 1940s to now, so it's 75 years later, we as chemists do not rely on any theoretical framework when we make new materials. So it's a semi-qualitative game. So you're using basically a couple of these tricks, like the one that I showed you here, supersaturation, you know, the addition of additives. So these are the little tricks, but there's no actually quantitative framework which you could use to guide yourself in the process. So in a way, you know, you must be familiar with the story from Mundaka Upanishad about the bird who's, you know, tasting the fruit of that tree, and there's this solemn bird on the top of the tree, and so that bird is always, you know, looking up and aspiring to reach that bird, and the bird is you know, alternately tasting the bitter fruits and the sweet fruits, right? All until at one point she realizes that actually she is that bird on the top of the tree. And so the same is here. It's kind of a constant trial and error. You have to, you know, just randomly pick things. You know, I mean, I say randomly, but you know, you randomly within specific windows of, you know, conditions, until you hit the right spot and you actually realize, hey, we made it. You know, this is it. So it's kind of, you know, some people say it's stepping in the dark, but that's what it is, and that's what it is. And I think in the foreseeable future, we're not going to see anything, you know, any model, you know, coming our way soon, because simply the chemistry is far more complex than, you know, than any physical, you know, theories can address for. So this is another, just, you know, I'm going back to the supersaturation thing, and you know, a proof came from space. Proof came from space. I mentioned it yesterday, and you know, it was realized that when you run a precipitation reaction under zero gravity, and in, you know, under these conditions here, the crystals are very different. And that's the consequence. That's actually an intrinsic proof that supersaturation is, you know, not uniformly distributed. It's dependent on the convection, and so so you know, that's just a natural effect. It's also, you can like pH, for example, if you measure pH next to the vessel wall, and you move from the vessel wall towards the inside of the solution, you'll realize actually the pH changes by a couple of units. So and the same is here, you know. So these things are very difficult to predict. So now let's move to another effect. This is the kinetics of the growth unit transfer. So when I say growth unit, you can think of that as atoms that are coming to a crystal and, you know, adding up. So this crystal is growing, and the atoms are coming to the surface of the crystal and making the crystal grow. So you have a picture here. So these would be the growth units. Again, you know, ions, molecules, whatever, and they come to form a crystal. So the crystal is there, and they are coming to the surface. Now, you can break down this process to a couple of stages. So these are the stages. So let's go from this stage, from the solution to the crystal. So you start here in the solution, and, you know, your growth unit is dissolved. It's solvated. It's surrounded by the solvent molecules. It has to cover the first energy barrier. The first energy barrier is the diffusion through the solution. So it has to diffuse. It has to find a way through the crystal, to the crystal. Once it does that, it crosses the first energy barrier. There's another barrier, that is the absorption. Okay, so it comes to the crystal, but it has to physically bind to the crystal. Absorption is a physical bonding. It's not chemical bonding. Okay, so so that's the second barrier. It's higher. Then the third barrier is dehydration. So dehydration means that basically it's a reminder that all these growth units, all these ions in the solution, are not moving through the solution by themselves. They are actually taking this sheet of water molecules everywhere with them. That's why when you measure the radius of these ions, you always have a hydrodynamic diameter, which is basically the diameter of the ion plus that solvation shell. So, but in order for that ion to be bound to the crystal very firmly, it has to shed this, you know, water sheet, and that's actually a highly energetic process. You know, so it has a huge energy barrier associated with it. And then there's the next one. There's a surface diffusion. Why surface diffusion? Because once the atom is on the surface of the crystal, it's bound. It still has to find the most favorable position. So it has to diffuse around, explore the surface, and say like, okay, this is the most energetic position. I'm going to be equally separated from all of my neighbors, you know, and I'm going to rest here. And so that's another barrier. And then there's the next one. There's active site incorporation, where actually, you know, the atom really gets incorporated into that. So the bonding occurs there, typically chemical bonding at that stage. So, and, you know, after that is done, everything else, you know, kind of is, you know, spontaneous. It's kind of, it's telling you basically that, you know, this is a sketch. Okay, so like all reaction coordinates, it's a sketch. So don't take this graph too literally, but it's giving you a, you know, nice qualitative scheme as to what is happening. But anyway, the crystal is at a lower energy state than a solution. So it's kind of telling you that it's, you know, the process of formation under these conditions is energetically favorable. So the slowest step is always the rate determining step. And this is the thing that I always do. Unfortunately, I cannot walk from here, so I cannot shake hands with you or you or you. So, so you will have to trust me, and you have to imagine me walking down this aisle and do all these steps. Okay, so I leave my notebook, I make steps, I extend my arm, I shake hands, I find your hand, and I shake hands, and that's it. That's the process. So, so kinetically, they always, sometimes you will read about these things, and they will tell you, so this is the slow, this is the kinetically critical process. You know, this is the rate determining process. So how do you know what's the rate determining process? It's the slowest, yes, it's the slowest step. So, you know, so under different conditions, really, this hypothetic reaction of or a metaphor of a chemical reaction of me coming down, shaking hands with one of the students is it's kind of, it's telling you that, different reactants in different environments would give you, different critical steps, different, rate determining steps. So if I was a very slow teacher, I would walk down very, very slowly. That happens sometimes, especially when you work with macromolecules, which are very massive. They take a long time to diffuse through the solution. Or if the concentration is very high. It's like being at a party, where like it's so dense, you can't move. And if you want to move from a point A to point B, you see a friend on the other side, of the room, and you want to go there, but it's so crowded, it takes forever, right? So diffusion is actually, it's not a straightforward phenomenon, because on one hand, if you increase the concentration, the diffusion rate increases. But if you go over the, some kind of optimal amount, it's going to get slower down. So if this room was very hazy and it was super loud, and if I know where my student that I want to shake hands with is, and I go there, and basically I can't find your hand, it's just I don't see anything. That's going to be the rate determining step, which is in a way I as an atom come to the crystal very fast, but then I take such a long time to actually find the most optimal place on the surface. So that kind of process will be called the surface determined step. So in that case, the surface reaction determines the whole kinetic process. So this is what I mentioned, that dehydration is the most energy intensive step. It's one of the outcomes of that is that very often the hydrates are much more easier to form than anhydrous compounds. Okay, so because oftentimes the atom is not even is not even able to actually get rid of that hydration shell, so it gets into the crystal together with the hydration shell. So you end up with the water inside of the particle. And so so if you look at some of these materials, you realize that hydrates exist at lower temperatures, and in order to get anhydrous molecules or compounds, you need to actually increase the temperature. So you need to provide more energy to the particles to get rid of that water. So you can read about this. And so example of a paradigm shift. This is a very interesting thing that I want to tell you. So from what I told you up till now, you might have an idea that particles and crystals grow with the individual attachment of atoms. So you have a crystal like this, sheet of paper, and individual atoms would come and get there, one atom, another atom, and so forth. And so that's what people used to believe all until say a couple of decades ago. At that point, a few scientists here and there started questioning this because that was a paradigm. That was a paradigm, and everybody thought it was true. That's how crystals. That's really intuitive, and that's how crystals must grow. And so one of them was my previous advisor, who actually, spent almost his entire career convincing the chemistry world that crystals do not grow that way, that they grow by following a completely different mechanism. And that mechanism is called aggregational growth. So the one that I showed you just now with individual atoms is called diffusional growth. So the atoms diffuse through the solution, come to the crystal, and that's it. But aggregation actually involves the nucleation of primary particles. And those particles come to the crystal, and they get tied to the crystal. And then it's kind of like building a house using bricks. So you put one brick over the other, and somehow that space between bricks rearranges, and so they become one brick. A coalescence of particles is actually involved in building these bigger particles. And so one of the critical proofs came with these in situ electron microscopy techniques, like the one you have here. So this is the video of a crystal. So this would be a crystal, and this would be a particle. And this is a different time. So this is 510 seconds, and the time increases here, and then further increases here. So you see the particle here, and this is the same particle, and this is the same particle coming in contact with the crystal, and here is also coming in contact with the crystal, and here as well, and finally it merged with the crystal. And so seeing this was kind of, wow, mind-opening, because this is, when you see something like this, then there's no question about that. So this effect is real. Before that, really chemists and physical chemists had a hard time imagining how, a solid particle and a solid particle could come together. These are like two bricks, right? They cannot, kind of blend into each other. It's really counterintuitive, but these are the things that are happening. And so this is the, one of the schemes that describes. So you go from ions to nano-sized primary particles, and so they, form crystals, and they coagulate, or they do diffusional growth. So so this was the precipitation, and now we can go through others, so other methods, and so one of them is the biomimetic synthesis. So what is biomimetic synthesis? It's kind of a precipitation which is very intensely surface controlled. So so you have a surface which is, a nucleation surface, biological surface, and all these properties like lattice geometry, topography are influencing the growth process. So you have, I think they said 5 minutes they showed, and so I think right now it's about 3 minutes. So we're gonna make a break in 3 minutes. So so these would be the organic matrix, and so these would be the nucleating crystals. And so if you look at an energy plot, you realize that actually, if you have the matrix, you realize the process is much more energetically favored. This drop occurs much earlier. So so in a way, this is how biology is synthesizing materials. And biology, we know now, can synthesize fabulous materials. Like if you look at spider silk, you realize that the tensile strength of spider silk is like much greater than steel. So it's the strongest tensile, the strongest material in nature. So one of the problems with spider silk, I don't know if you know, like why don't we have much spider silk, is because you cannot domesticate spiders, right? They are very difficult to domesticate. So that's why we use silkworm silk, which is not as strong as the spider silk. So, but anyway, so biomimetics is a very, very powerful thing, because it gives us, it teaches us how to create these materials. So a lot of scientists spend extraordinary effort, exploring these methods. So annealing, and I think after annealing we're gonna have a break. And so annealing is the most traditional method for making materials. So it's called beat and heat. That's the the kind of the funny term. So what you do, you basically take a mortar and a pestle, you get the powders, you mix them, and that's why you kind of beat that, and you rely on crude mechanical manual force to homogenize the precursor powders. You press them into a pellet, you put the pellet into a furnace, and you set the temperature, and you let all these powders chemically react, and as they chemically react, they form the material. And so this would be the typical material. This would be the typical microstructure. What do you see about this microstructure? Yes, it's very heterogeneous. Yes, it's very coarse, as material scientists would say, which means you have a lot of big grains, a lot of small grains, not very pretty. And typically the size here, do you see the scale? It's 10 centimeters. So so what is the what cannot you avoid using annealing? You cannot avoid the coalescence of individual particles. So you want to have a nanomaterial, you want to preserve the individuality of these nanoparticulate units. But if you provide so much thermal energy, and most of the time you need a lot of thermal energy to run a chemical reaction, you actually bring a lot of energy that's going to promote the diffusion of these atoms, and they're just going to blend. That effect is called sintering, and I mentioned that a little bit later. So so this is definitely not an ideal method for nanoparticles, and that's very rarely used. So did you say break?
Yes.
Okay, so we're going to continue. I think we're about halfway through this, and so we're going to have some next hour, and then the next 2 hours will be the characterization typically.
you're talking about that. That's very interesting. It reminds me this spider.
Oh, the spiders. So
Yeah, spiders. That tensile strength.
yeah.
So it was about 2 years. Yeah, we recently published a paper with two of my MTech students, MS students, a paper on biosteel. This is not our work, it's a review paper. I'm also very fond of review paper. And the main interesting thing in that paper is that the spider gene was impregnated in goat, and the milk of that goat, the kind of fiber, it is even, the tensile strength is even larger than steel. So it's called biosteel.
Wow,
It's
that's really
amazing
good.
thing.
That's really incredible.
I will bring that paper,
so that's a very good example of kind of like biotechnology, right?
biotechnology, it is
know.
you remember that? So it
Yeah.
was fascinating. And there is one company in the United States. They ultimately got that patent, and they have developed it and demonstrated. I mean, the thing which interests me most, the spider gene is proper impregnation in a goat can produce a milk like that.
Yeah, that's
And
incredible.
out of that, you make the fiber.
That's stunning.
That's fascinating.
Stunning. Really. Yeah. Very, very nice example. I think it's like, and then that's really like biotechnology,
That's biotechnology.
nano. Yeah.
Inserting a gene. It's a genetic engineering, of course, it's a genetic engineering. But how it expressed, it's a different host, but its expression is unusual. Okay, let's have some tea or coffee, whatever you have.
Excuse me, sir. I wanted to ask you something. Actually, I was working on dye degradation, organic dye degradation. So I was using rhodamine and methylene blue, and I was using my bio-origin nanoparticle for their reduction. So what we saw initially when we set the experiment, the reduction was being happened, at that time. But after 6 hours or 4 hours, the reaction was being reverted, as in the dye was regenerated in the solution. At that time, it is being degraded, or whatever the product is being formed. But after 4 to 5 hours, it's being regenerated. This is specifically for the and MB. We worked on not many dyes, and other dyes are working fine.
So the runway is like, it disappears?
Yeah, it disappears completely from dark blue to transparent
I see.
just after adding the nanoparticles
I see.
with
So-
sodium borohydride. So initially with sodium borohydride, the process is not happening, but after adding the nanoparticle, it's working very fast.
Oh,
But the problem is we don't know why it is happening. But after 4 to 5 hours, it's coming back. And we search for papers. There are not lot many papers which are talking about reaction which is happening after 4 to 5 hours. It's like, yeah, it is happening just after adding, but they don't know about 4 5 hours.
yeah.
So we accidentally we kept that reaction as such for 4 5 hours, and then we saw, okay, it's coming back.
Yeah.
So what could be the reason in that way?
I don't know. It's got to be some synergy between particles and the reduction agent and the rhodamine, right? Because but I don't know. I just can't tell. I think it's
I thought it would have to do something with the chemistry part only, because our particles are working fine, because initially this thing is happening, the reduction is happening. After 5 hours, what is happening? So the reaction is being reverted.
I see. So did you try to do everything without nanoparticles?
Yes, sir, we did,
These are
but
gold nanoparticles.
yeah, we used gold as well as AG nanoparticle. With
Okay.
AG, the reduction process is a little slow, but with gold, it's
I see.
so you can have this.
Yeah. It's hard to tell. I mean, man,
What should be done to solve this problem? As in, what should be the approach to go about it?
Excuse me, sir. So could you tell the difference between no matrix and with matrix? What do you mean?
So the matrix is. So the matrix means this organic surface on which the precipitation occurs. So that's what is kind of organic matrix, in a way. So I mentioned like heterogeneous nucleation, right? It's kind of more energetically favorable than a homogeneous one. So that is the effect of the organic matrix in a way. So typically these surfaces are promoting right nucleation. So nucleation happens more favorably on them. Yeah, on the matrix. So in a way, I think it's a little bit of maybe it's not a good term, the matrix, because when you say matrix, usually it means something three-dimensional, but in this case, it's just a surface. Okay. So it's a biological surface. So biological meaning, protein surface, like when you have formation of, say, bone crystallites, you have osteocalcin. That is the molecule. So that is the.
Sir, is it same as tissue scaffold which we use for this tissue engineering?
So with tissue scaffold, so it's not the same in a sense that tissue scaffold is a very three-dimensional structure. So organic matrix is more like a two-dimensional thing. But you can make tissue scaffold that's actually going to mimic organic matrix and actually promote crystallization of nanoparticles on it. So in a way, yeah, you can make that. Tissue scaffold can be kind of like a mimic organic matrix. So yeah, so it's the. Oh, I'm sorry, I didn't.
Start.
Sure, anytime you're ready. Shall I wait for myself here? Thank you. So can I just get reminded how much time I have? Because now it's 11:25. So when do we?
It is 11:25 now.
Yeah.
12:25.
So 12:25. Okay. So let's continue. So this is where we stopped. Now we go to chemical vapor deposition. So CVD, standing for chemical vapor deposition, is actually the oldest method used to make nanoparticles. So this is kind of a method that is a part of the history in nanoparticle synthesis world. So how does it work? The name is very explanatory. You have a chemical vapor, meaning you introduce molecules or atoms in a vapor. They come here from the left side as a gas flow. They enter a chamber, and inside of the chamber there is typically something like a cooling of the temperature. So these particles can fall onto a substrate, or something like this. You have a substrate here, and these particles are kind of falling onto the substrate, and you have a scraper that's kind of scraping them off the surface periodically. So that is one of the ways. So these particles introduce as a vapor, meaning that they come in very fine droplets, right? So each of those droplets is going to define the particle size. So if you have a droplet and only the ions that are inside are going to crystallize into a particle. So in a way, that's a very nice way of controlling the particle size, because you have these isolated droplets inside of the vapor. So sol gel synthesis is another, popular way of making nanoparticle. It involves, again, as the name says, a transformation of a sol into a gel. So technically speaking, you start with a solution, and the solution is transformed into a sol, and sol into a gel, and then you process that gel to get the particles out. So solution, right, involves what is the difference between the solution and the sol? What is the difference between the sol and the gel? Do we know? So in a solution, your ions are hydrated and they're solvated, and so they are individual units. But in a sol, you already have particles inside. So these particles are suspended. So sol is the same as suspension or a dispersion. It's a colloidal, basically, term. So you have a sol here, and so what is the gel? What is the difference between a sol and a gel? In a sol,
It's a network of particles.
Liquid dispersion solid.
yes, exactly. So that's the difference. So sol is, I mean, you were right too. But this is when we talk about the difference between a sol and a gel, it means, sol is the dispersion of a solid in a liquid, and gel is the other way around, right? Like cheese is a gel, and mustard or ketchup are sols, or milk. Milk is a sol in a way, well, sort of sol. So you need to have a solid particle inside of the solution, and in case of milk, these are all these, fatty globules. So you have that transition from sol to gel. What happens is that these particles are actually starting to kind of, aggregate. This is a method that works well with silica. So you have silicon network forming, and as the network is forming, you start with these silica particles, and they start to form a network, and that network turns into gel, because that at one point that network becomes so dense that you have actually more solid than the liquid. And then you can evaporate the liquid, and you end up with these, kind of patterns that, they're called zero-gel or dense ceramics. Or, in a solid stage, you can actually even deposition of these particles onto a thin film. So there are different ways, and, sol gels is kind of like a composite method. It covers a bunch of, depending on which way it branches, it could be really just a thin film deposition or, or real sol gel. So let's skip this. Is giving you more information. So electrochemical processing is also very popular for some types of materials. Okay, for what types of materials? For metals, because what you do, you are actually transforming the electrode into a nanostructured material, and the electrode is, metallic, right? So you do, you have a, kind of electrochemical cell or improvised inside of your, beaker. And so what you do is you have, a reaction on an anode and a cathode. And so typically you can use cathodes such as aluminum, or you can use titanium. These are very popular choices. Why? Because you can create, in case of aluminum, you can create these, very nice gratings. You actually get an etching effect. So there are two ways you can run the electrochemical processing. One of them is deposition. So you start with the electrode and you can deposit things onto it. And the other way is the opposite. It's actually you are taking away material from the electrode. That is called etching. So in case of deposition, you can grow wires, very nice nanowires on the surface of these electrodes. And in case of etching, you can have the opposite effect. You can actually etch these nanotubes. So, so nanowires versus nanotubes. And you can create very nice materials, very nice morphologies. They're shown here. These are nice nanowires, and they're very, very pretty, kind of uniformly distributed, nanotubes. Again, how it works? Well, you play with the conditions, right? You change the electric current, you change the concentration, and then hope that you're going to get something like that. So spray pyrolysis is, in a way similar to chemical vapor deposition, because it's happening, in an aerosol. So what happens here? This is a lab, and this is a spray pyrolysis setup. So you have a solution here. Okay, so in this beaker, and so you put the ultrasound, and so this ultrasound is starting to vibrate and create little droplets. and these droplets are leaving the surface of the solution and going up into this tube here. See the tube? And so the tube leads to a furnace, and you are actually heating all these individual droplets of the aerosol. And as they heat, they form particles inside, right? It's a natural process. And then, they basically fall here, and then you can have multiple setups. You can have one temperature for one type of reaction, and then they can lead to another. So, you can play around with these things, really. And you end up with something like this, because you are running a reaction inside of a droplet, and a droplet is spherical, you're going to end up with spherical particles. And that means usually it's going to be very pretty, because people love to see spherical particles. And so what is the problem? The problem is that using the ultrasound, you cannot lower the particle size infinitely, right? So you can hardly make it to the nanoscale, if ever. So this is a typically microscale technique. So you can play around. You can really lower the concentration of your ions in a droplet, but that's just gonna, kind of be an ad hoc solution. So very difficult to lower down below 500 nanometers. And is the particle size of 500 nanometers a nanomaterial or not? By convention, it is not, because 100 nanometers is, is the limit. But in medicine, people often say, that everything below 1 micron is actually a nanomaterial. So it depends where you want to report your data. If you want to go to a material science journal and you have 500 nanometer particles, it's not going to fly with the reviewers. They're going to say, this is not a nanomaterial. But if you go to a medical journal, they probably will accept that. So photolithography is another, useful method. So this is this is how it works. This is a very simplified setup, and I think it's important for you to know just the basics, because this is such a pervasive method, and it's used everywhere, from the computers to microfluidics. So what you do, you start with a silicon wafer. This is silicon, and you put sometimes you put this temporary coating, it's Omnicoat, but eventually you end up with this SU8, which is a photoresist. So it's kind of a polymer that is getting polymerized by ultraviolet light. So again, depending whether it's a negative or positive photoresist, it can either be polymerized or depolymerized using ultraviolet light. So you put the grating, you put the mask on top of it. See, you put the photo mask and you apply, ultraviolet rays. And so if it polymerizes only where, it gets into contact with ultraviolet rays, you're going to get a pattern that is defined by this mask. See the yellow here. And then you can create, different types of materials using this. So you can put all kinds of polymer on them. So in this case, this is silicon, PDMS. And then silicon can end up as a template for another polymer and so forth. And these are the patterns you get, kind of very periodic. You can get pillars or wells. You can get different shapes. In this case, these are kind of some pillars that are, kind of rectangular in shape. You can get spherical, you can get pyramids. And it's a huge effort right now in biomedical science actually to study the effect of these topographies on the cell fate. How does it affect, cell metabolism? How does it affect the differentiation of the stem cells and so forth? So very, very popular. So another technique that leads to similar materials is inkjet electrospraying. It's kind of like what you have in inkjet printers. You have a jet that is, programmable. So basically the positioning of the jet, is easily programmable using, a software. So you can create all kinds of things. It's kind of, you have a syringe in a way, and then you are, you're projecting this onto a surface, and you can, write things. It's kind of like a pen of a kind, right? Again, it's very difficult to go down. So this is what we talked about yesterday. So I'm going to skip this. Another method is the mechanochemical synthesis. So mechanochemical is not considered very elegant. Why? Because it's happening in a mill. So you put things in a mill and then you just mill. So it's kind of a traditional way of making materials, but it's a very good way of making nanomaterials that otherwise cannot be made by precipitation. And let's assume I personally use this method when I wanted to create material that requires very high temperature. So you create a material at a high temperature, and then what happens at a high temperature? All these nanoparticles start to aggregate, and you want to break these aggregates again. So you put them in the mill, and so these little black dots are powders, and these balls are actually what's spinning inside of the mill. And the collision between the balls, when the powder is found in between the balls, leads to breaking down of the powder particles. So in a way, it's a very robust process. And you can break these huge agglomerates into smaller ones, and you can end up with nanoparticles. But what is the problem with this synthesis? So it's been actually used a lot even in pharmaceutical industry these days, because you can amorphize drugs, and now we know that if you use aspirin or painkillers, they become absorbed much faster if they are amorphous. So you would create particles by precipitation, and then you put them in a mill, and then you mill them like forever until they get into amorphous state. So, but what is the problem? There are 3 central problems, and I really make my students be aware of that always. They know that. So one of them is the contamination issue, because you cannot avoid it, because all these balls and all the vessel walls are always going to contaminate the particles to some extent. However, there's a solution to this. There's a solution to minimize that, and particularly if you use tungsten carbide balls, you can minimize the contamination. So be aware of that. So tungsten carbide is a very, very good solution for this. And that's what is being used in the pharmaceutical industry, actually. So another problem is the problem of aesthetic nature in a way, but also functional. Because remember, spherical particles are kind of prettier than these coarse particles that are all over the place. But also sometimes you want to have the particles to function the same. And when they're all equal, we call them monodispersed in a way. So they're kind of, every particle is equal. That their functionality is not going to vary from one particle to another. But when you have something like this is a typical morphology. You have very ugly particles. And I showed it earlier yesterday, actually, that sometimes you can get a better effect using these particles. But most of the time, actually, you don't. It really depends on the application. So in this case, you see that the particles are very regular, and that is the direct consequence of collision with these balls. So as they collide, they always kind of break the particles into this irregular shapes. So these are the central problems. Another problem is that actually the local increase in the temperature. So you can't really use organic molecules, right? So anytime there's something that's sensitive to temperature, forget it. So it cannot be used for mechanochemistry. Okay, hydrothermal synthesis is a way of synthesizing materials at A, high temperature, and B, high pressure. But so think of that. You want to create a material that requires 1,000 degrees. So hydrothermal synthesis was actually designed to synthesize these very same materials at, say, 200 or 250 degrees. How? Because you increase the pressure. So that increase in pressure is compensating for the lower temperature. So yeah, you can actually make particles at lower temperatures and avoid their extensive agglomeration. And that is, very cool. So you can see some of the particles. You see how they look. And I can't see the exact scale from here, but this one is 2 microns, which means the particles are about 2 microns in this case, and this is 1 micron. So you can definitely create nanoparticles. And you can see that their shapes are like fantastic. I mean, totally like resembling the, the unit cell. So kind of which is what crystallographers would call equilibrium crystal shapes. So so it's, you know, typically the temperature range is, you know, 100 to 374 degrees, because that's the critical temperature of water. You know, you can, you know, if you increase the temperature, if you increase the pressure of water, you decrease the boiling point, right? So, but you know, 374 is as high as you can go. So Langmuir-Blodgett technique. So that's, you know, layer by layer. So that's, you know, a popular technique for surface deposition. Okay, so if you want to have a nanoscale thickness, now remember, what makes a nanomaterial is not necessarily a whole particle smaller than the 100 nanometers. You can have a particle that's as big as from here to the end of the room, and as wide as from between these two walls. But if the thickness of that particle is smaller than 100 nanometers, it's still going to be a nanoparticle. Okay, so it has to have a less than 100 nanometers in at least one dimension. So, like for example, if you look at the enamel crystals, they're very long. They could be a millimeter long, these hydroxyapatite crystals, but their diameter is about 20 to 60 nanometers. So despite their, you know, kind of, you know, millimeter length, they are nanoparticles. So in this case, what you do is actually you have a solution, and then you put a surfactant. You know, what is a surfactant? It's a long molecule that has one polar head and non-polar tail. So, and then what you do is you just plunge a surface, you know, like a, you know, substrate into that solution. See, it goes in and it goes out. And so as it goes out, basically it absorbs these polar heads of these molecules. And so you can do it again. And in that case, because the non-polar tails will be on the surface, it's going to absorb non-polar tails. So you can actually, the number of times you plunge this substrate into the solution is going to determine the number of layers you're going to have. So you can, you know, say if the length of one surfactant molecule is about, you know, half a nanometer, you know, like if you plunge it 10 times, you're going to have 10 times 1/2 of a nanometer. So you're going to have a 5 nanometer like thickness of the film. So so that is a very elegant thing. And actually, there's a story about that technique. It was really derived in a kitchen. It was derived in a kitchen, and that scientist, it was a female scientist, and she sent a letter to Langmuir, and she was curious whether that was the, you know, whether she did something significant. And then Langmuir took that method and refined it, and nowadays it's known as Langmuir-Blodgett technique. But actually, it was derived by a complete amateur, you know, like a chemistry enthusiast who was just practicing. It was about like, you know, almost 100 years ago. And there's a combinatorial techniques, you know, so you can always combine multiple techniques. In this case, it's a mechanochemistry plus precipitation. So so I mentioned that this comes from my research. So lanthanum strontium manganites, in this case, you know, they cannot be made by precipitation. You have to go very high in temperature. So I would basically, what I would do, I would anneal them at like 700, 800 degrees. But I needed nanoparticles. So, you know, I would go back, put them in the mechanochemical reactor, grind them for long periods of time. And you end up with something like this. The particles are very ugly. Let me notice that, because they're very regular in shape, right? That's the consequence of, and then I would coat them with silica. So you simply put like a silicon, you run a polymerization reaction, really simple chemistry. And then you end up with kind of like particles that are protected with a silica layer. So what is the purpose of the silica layer? It prevents the agglomeration of these magnetic particles. The particles are magnetic. They have a huge tendency to agglomerate because they're attracted to each other. So you want to minimize that, and also you can provide a biocompatible coating, because silica is biocompatible and lanthanum strontium manganite is not by any means. This is another example where you can actually run a precipitation chemistry in this window and then use it as a substrate for actually as, you know, as a substrate in a way for lithography technique. So, you know, so all these techniques that I mentioned can be really, you know, combined. You know, so this is another example where you go a top down, you have, you know, lithography method, and you have bottom up, you know, self-assembly. So basically, you're kind of self-assembling something on a surface and then adding up the lithography method. So really, there's no, and I mentioned this yesterday, so we're going to skip that. Now, so we talk about methods for synthesis. I picked a couple of them that are typically used to make nanomaterials. Now, very often you will hear people talk about processing. And very often they confuse the synthesis and processing. And they interchangeably use the two terms. And that's common among material scientists, believe it or not. I think that 3/4 of the material scientists, if you ask them what's the difference between synthesis and processing, they would not be able to tell you. But I'm telling you this. So synthesis means the making of the material, in the first place. And processing means refining that material and preparing it for the application. So in a way, it's a post-synthesis process, So if you precipitate a particle, you take that powder, you isolate the powder, and you have a powder, and then you can do something else to that powder to make it more, probable for application. So the first method for sintering the first method of processing I picked here is sintering, because sintering is very common. You cannot imagine any electronic device without sintering, because all these powders, right? You can't put a powder in an electronic device, right? You have to, deposit that powder and you have to sinter that. So what is the purpose of sintering? What happens during the sintering? So this is what you start with, kind of like nanoparticles, and then you reduce the pores. You make them sinter. Of course, this works for materials where you don't want to have their discrete nature. So sintering is very often the opposite of maintaining the nanoparticular nature of powders. So as you increase the temperature, you reduce the pores, and that's what is called sintering, this coalescence of these particles. So the thermal treatment is another thing. When do you want to thermally treat your particles? What happens when you actually thermally treat particles? What do you impart to particles? Energy, yes. So yes, so you are actually making them diffuse more, right? So more energy, thermal energy. Thermal, right, is temperature. What is temperature? Temperature is the measure of the movement of the particles, right? So if you increase the temperature of the material, these atoms are going to move faster. So if you have a crystal lattice like this, now when you precipitate the material, you will never get a perfect crystal. This is one of the outcomes. You will always get a lot of defects. And this is how a highly defective crystal structure looks like. You have a lot of these, holes. You have like vacancies, interstitial atoms, these red things here. So you increase the temperature, so these atoms start to move around. And as they move around, they are free to roam and find the more optimal positions in space. So after you increase the temperature, you get a more perfect crystal lattice. So that is one of the points. And very often you increase the properties. Let's say if you have a magnetic material and your properties are highly dependent on the the distance and on the crystalline symmetry of the material, you're going to benefit from that. So mold casting, I think we can skip that. Electrospinning, if you have a material, and I mentioned electrospinning, this is, you have a syringe and you have a substrate, and you have a electrical potential difference between the substrate and the tip of the syringe, and that difference in the potential, which is voltage, is kind of driving the movement of these threads, and they become deposited on this screen. So it's very good for making scaffolds, as you mentioned, because to make a scaffold, you need to have pores in a material. And so this is one of the mainstream methods for making scaffolds. Because why do you need pores? The cells need to grow somewhere, right? So if you work with a scaffold. Doping is another thing. You want to dope your material sometimes with other elements. Why? Because you want to improve certain properties. Let's say if you work with steel, you can dope steel with anti-corrosive elements, so you can reduce the corrosion rate. So in this case, this is exactly it. You have here from left to right, we have an increase in the weight percent of chromium, which is the anti-corrosive element. And you see that as you increase that, the corrosion rate, which is given here, you see it's dropping down here. And then the resistivity goes up, and the magnetization actually goes down. Now, it's always a trade-off, right? If you want to have a magnetic material, whatever you do, so whatever the dopant you add, you'll have a trade-off. One property is going to be improved, but it'll be a sacrifice for other properties. So, so another thing I want to mention is the rapid prototyping. Now, this is a term you might have heard of somewhere. So, what is rapid prototyping? It's it's one of the future of medicine. It's one of the future of medicine, and it's a way of synthesizing materials that really fit a particular need, say a patient. So this is one example. What you do, you run a CT scan on a patient to look at say a defect in bone, for example. So you look at that defect, you have a very nice three-dimensional picture, and then your computer program is going to automatically create an AutoCAD model from that CT scan. And that model is going to directly replicate actually the shape of the defect. And that model is going to feed into the automatic, say 3D printer, scaffold fabrication, whatever it is. You can have, inkjet printing or anything like that. And then, so you basically sit by a computer and everything is run. You analyze the patient and everything else is automatic. You end up with a material that's directly replicating the defect. So why do we need that? People say that every patient has a different jawbone, for example. It's directly applicable to dentistry as well, or oral medicine. So if you you don't have two patients with the same identical dimensions of the jawbone. So whenever you have to add an implant to that, it's very good to have that, because otherwise the surgeon has to open the bone, has to look at the defect, and then has to in situ determine what is the ideal bone graft and so forth. So that is the future of the creation of of materials. The fun fact, so my students know that at the end of every lecture I give them a fun fact. So this is one of the fun facts that I really like. So typically, if you look at a crystal and it grows, so if a crystalline phase grows very fast, what's going to happen? If a crystalline phase grows very fast, it's going to disappear from the crystal. This is shown here. So you have these two phases, X and Y. So let's assume that X is growing slower than Y. So as Y is growing, actually, it's going to contribute to, so these atoms are going to be added to I much faster than to X. So what happens as it's growing, Y disappears. Y disappears. That's an effect that we see actually with a lot of cubic crystals that turn into octagons. So I think Friedrich Nietzsche said that everything, like all the smart intellect, all the great intellects are like fountains that take a very long time until they realize what has fallen into their depths. So basically it takes time to realize, so everything that grows very fast, withers very fast too. So time is needed. So anyway, so let's go to the next part, which is characterization. So in the previous hour and a half, we talked about the methods for synthesis of nanomaterials and some of the materials in general. Now, what comes next is you have to characterize, right? You can't just synthesize something and it's going to stay in a beaker and you would not even know what it is. So you have to look at that. You have to look at that and you have to provide a proof that it looks the way you want it to look. Now, there are different methods for looking at the materials, and there are also all these methods are looking at a different element of the material structure. Now, material structure is not one thing, right? So material structure itself is being characterized by multiple, you could call them parameters or quantities. So they're listed here. So you have a chemical composition. That's how you start to characterize something, right? You want to know what atoms or molecules make your material. That's the first choice usually. But even though you know what's inside of your material, it doesn't really tell you more. Like if you know you have carbon, okay, you have carbon. Is it graphite or is it diamond? Is it C60? Is it nanotubes, right? What is it, right? It could be so many different things. And they differ in properties immensely, right? If you look at calcium carbonate, it could be calcite, it could be veterite, it could be aragonite. And these are also, different materials. So then you go to crystal structure. You want to know what is actually the symmetry of the arrangement of these atoms inside of. So you want to know how they are arranged. So we need to characterize the crystal structure. The next thing is crystallinity. And actually, I even give here the methods that are typically used for this characterization. And we're going to talk not about all of them, but about some of them. So crystallinity is, telling you essentially, how crystalline the material is. So it's different than the crystal structure. When you look at a crystal structure, it's just going to tell you the symmetry. It's going to tell you, what is the space group, what is the symmetry in which these atoms are ordered. But the crystallinity is going to tell you the degree, like how well ordered they are, how many defects you have, what is the amorphization degree. So that is crystallinity. If you have ultimately high crystallinity, it means perfect crystal lattice. And if you have, ultimately low crystallinity, it means completely amorphous structure. So particle size, that's another thing you want to know, right? Because that's really important, especially when you work with nanomaterials. It's going to tell you whether your material is a nanomaterial or not. Polydispersity, what is polydispersity? It tells you the distribution of the particle size. So that distribution of particle size can be very broad, which means that you can have, your average particle size could be 50 nanometers. But if your sample is very polydispersed, it means you might have a particle that is 1 micron and particles that are 2 nanometers. So on average, it's 50 nanometer, but you have a very, very broad distribution. But if your sample is monodispersed, it means that almost all particles are 50 nanometers in size. So that's quite important. More porosity is another thing, which means, once you press your particles, into a sample, what is the pore size? Is there any space in between the particles? Like, can you grow cells? So that's very important. If you have high porosity, hey, we can use this as a scaffold. If there's no porosity, hey, if we put this inside of a human body, no cells could proliferate there. Morphology is going to tell you about the shape of the particles. Surface structure, again, it's highly important because surface is most of the time completely different than the interior of the particles. So you want to characterize surface separately, because and surface is the thing that is interacting with a biology, as we'll see tomorrow, actually. And finally, the concentration tidal defects. So what is important to keep in mind is really every characterization technique is partial. So it's going to tell you information about one aspect of your material. There's no characterization technique that's going to cover all these elements of material structure that I mentioned. So in a way, you must know the story about the elephant in the dark. Or there's another version of a story where blind people touch the elephant, right? You know that. So you have a couple of people that are basically touching the elephant in the dark, and one of them is touching the, this what's called the nose, the trunk. So he says, "This is a snake. I'm holding a snake." The other one is touching the trunk, the tummy. He says, "This is a pillow," right, or something. So another one is touching the leg. He says, "This is the trunk of a tree." And so they start to argue, and they say, and everybody thinks they're right. And but only when they come together and combine their perspectives do they realize that actually they were touching an elephant. And the same is with characterization of the materials. You need to get the input from all these multiple methods. and then put them side by side and analyze them and say, okay, because otherwise you're going to be tricked. You might be thinking you have a snake instead of an elephant, or a pillow. So I give one example about a particle size. These are the 3 methods that you could use. So typically, if you use XRD, it's going to tell you the crystallinity. So crystallinity may be equal to particle size or may not. If you use dynamic light scattering, it's going to tell you hydrodynamic diameter. And it's going to, if you use transmission electron microscope, you might see aggregates actually, and you might be tricked. So okay, so let's start with the microscopy techniques. These are the basic terms, and I don't think we need to cover them. Contrast and sensitivity and resolution. So these are really, really basic things. So you might be familiar, but so let's switch to electromagnetic spectrum. I'm sorry. Oh, they're not changing. Oh, I didn't notice. Okay. I apologize. Okay, so let's go back. So these are the elements of the material structure that I talked about, and these are luckily you have the book in front of you, and these are the methods, and then we cover the story about the elephant, and then we go to microscopy techniques, and we're going to skip that because this is not really essential, and this is something for your information. When you look at these material later, just to as a reminder to remind yourself what is the electromagnetic spectrum. And it goes from very, very long wavelengths like radio waves, and it goes to very, very short wavelengths like gamma rays, which are the shorter ones. And somewhere in between, there's this region that we call visible light, 300 to 700 nanometers. That light, as people often forget, is not visible outside of us. We make it visible. We evolved into these, cognitive systems that are actually assigning visibility to that frequency range. So there's no such thing as green light or blue light outside of us. It's just wavelengths, But we decided as we evolved that actually these are very meaningful colors, right, and meaningful frequencies, and that we could actually, navigate ourselves through the world by seeing them. So 300 to 700 nanometers. Let's skip this. This is not really important, and we'll skip that. So 300 to 700 nanometers. This is the wavelength of the visible light. And so so if you want to see an elephant, using an optical signal that has the wavelength of 5 meters, say the size of an elephant, would you be able to see the elephant? You won't, because the wavelength of the light has to be at least equal or smaller than the size of the object. Otherwise, you can imagine that as like kind of just hopping over the elephant, right? So the same is here. If you have a particle that's 1 to 100 nanometers, and you use the visible light, whose wavelength is 300, at least 300 nanometers for violet light, almost ultraviolet light, you won't be able to see that particle, right? You'll see some hazy, pattern. So, and that's why we need electrons, because with light, you cannot speed light beyond the speed of light, right? But electrons can be sped up. And you can not beyond the speed of light, but and if you look at the de Broglie relation, which is given here, you can, or actually here, this is even better. You can see that the wavelength of any object, and electrons, remember, are both waves and particles, just like photons are both waves and particles. So the wavelength of electrons is directly proportional to the Planck constant, which is a constant, and inversely proportional to the momentum. And the momentum is the product of the mass, and the mass is the constant, and the velocity. So if you increase the velocity of the electrons, you're going to actually drop the wavelength. And as you drop the wavelength, you can actually go down much lower than 100 nanometers. And you can see the objects that are smaller than the wavelength of light. And that's why we need electron microscopes. That is the reason. So, so a simple reason. And optical microscopy is still used in materials, but again, only to characterize something that's bigger than the wavelength of light. You can see something like this. You can see this, and these are kind of like defects, but they're really extremely robust. And in order to see something like this, these are nanoparticles of I think this is boronitride alloy and titanium nitride. So see, this is 5 nanometer scale. So these particles are about like 2 to 3, 5 nanometers. In order to see information, sort of see the particles, you need to use electron microscope. And here you can even see individual atoms. Someone asked if these are the atoms, so I don't think those were, but here you can see them, and you can see them here as well. So all these little dots are actually individual atoms building up this crystal lattice. So in order to get this information, you need to use electron microscope. So electron microscope is the most powerful characterization tool for nanomaterials. So there's nothing that goes beyond that. Because if you visualize something, it's really you can tell a lot of information. You can tell about the crystallinity, you can tell about the particle size, you can tell about the defects, you can even tell about the surface. If you look at a surface and you can compare that. See, you have a defect here, you have a defect, right here. These, so there are multiple types of electron microscope. So have you covered this through your general education? Am I repeating this, what you already know? Yes? It's okay, okay. So so you should let me know. Just let me know, raise your hand and say like, let's go to something, else. So the first type is scanning electron microscope. And so how it works is, sometimes I ask my students, what is the difference between the scanning and the transmission electron microscope? And they tell me, well, the scanning one is scanning, and the transmission microscope is transmitting. And I tell them, well, it's a 50% correct, because the transmission electron microscope is really transmitting electrons, and that's how you're gaining the information. But it's also scanning, and the scanning one is also scanning. So so you didn't give me the correct answer. So so scanning just means going from along the screen. So creating a sample. So the way it works is so you detect the secondary electrons. So you are directing a beam of electrons onto the sample, and so these electrons are actually ejecting electrons that are called secondary electrons, and these electrons emerge from the sample and are detected by the detector. So so this is how it works. So you have this would be the the sample, and the electron beam comes from here. The secondary electrons are ejected, and the detector detects them. Oh, I'm sorry, I'm using the wrong. I'm not using the laser pointer. Okay, so this would be the detector, and this would be the specimen and the electron beam here. So you get a contrast. How do you get a contrast? Because heavy atoms have greater density of electrons, so more electrons will be ejected. So they're going to give more signal. So they're going to be lighter or darker depending on whether you inverse contrast or not. Than those that have that are lighter. So these are the images you get using electron microscope. You cannot really go lower than the highest resolution is 1 nanometer, and that's the high as high as you can get. So typically, you go much lower than that. You're like 20, 30, sometimes even 100 nanometers. So transmission electron microscope is another method where you actually really transmit the electrons. So for that purpose, the samples need to be what? Need to be thin enough. Okay, so that's why you typically do the microbeam. You cut them into very, very small sheets that are nanoscale, and you transmit electrons through them. And you can get much higher resolution. And so the heavier atoms are darker because they do not transmit electrons as well as the lighter atoms. That's how you get a contrast. You can get phenomenal pictures with the atomic resolution using the transmission electron microscope. So this will be the overview, comparison. You can really read about that, later. So the resolution is really different. You see the resolution for transmission electron microscopy is 0.2 nanometers. So you can really visualize not only individual atoms, you can visualize actually orbitals. So for scanning, you can see it in individual atoms. You can't. And for the optical, you're far behind. So the third microscopy technique that we're going to cover is also essential for nanoscience. It's atomic force microscopy. It's very comparable to the way record players work. I know you're a younger generation, so I don't know if you still have record players. But when I was a kid, I played only records, and later the tapes came, and after the tapes came the CDs, and then after the CDs, then the MP3s and so forth. So in any case, it's very similar because you have a sample. Here there's a sample, and you have a cantilever, and on top of that cantilever this would be the cantilever, and this would be the probe, a very, very thin nanoscale needle, kind of like the record player needle. And it's running along the grooves of the sample in the same way the record player needle is running along the grooves of the record is making a sound. So you have the same effect here. Now, so one of the things is that, like, how is the signal produced? I think I have it on the next slide. So you have I know this is a very, very complicated, but I'm just going to focus on this little detail that I want you to know. So this is the sample, and the sample has some topography. So let's say you have an array of nanoparticles, like here. See, you have a bunch of nanoparticles on it, and their diameter is about 30 nanometers, as you can see from here. So as this needle is running along them, it's kind of this cantilever is being deflected. And so there's a laser light shining onto the tip of the cantilever, and the deflection of the cantilever leads to the change in the angle of the reflected light. And so the reflection of that light is being detected. Now, so there are multiple ways that are actually controlling the deflection of the cantilever. So one of them is the electrostatic force. So the way it works is somewhere like here. So you have, so this would be interparticle potential. This would be the attractive region, and this would be the repulsive region. So you're kind of like in between. You have to come close enough, you have to approach the sample with your, a tip of that cantilever close enough so that the electron clouds start to overlap. So the approach is extremely, extremely fine. And so at that point, you can sense this, electrostatic attraction. And that is what is actually driving the finest movement that are detectable. There are multiple ways. There's, you can often hear about the contact mode and the tapping mode. So the contact mode is kind of like a record player. It's just moving. With the tapping mode, you're doing constantly this. You're tapping the sample. So why do you need the tapping mode, and what are the samples that you want to analyze with the tapping mode? What do you think? So organic samples like proteins or stuff like that, biological molecules. So if you have a biological sample, you want to avoid actually, move, because if you constantly run a sample, you can just start moving those particles that you were observing together with a tip. And if you're tapping, you're avoiding that, right? So you're minimizing the drag and the artificial signal you will get from that. And when you have a very robust sample, like a nanomaterial of metallic or ceramic nature, then it's totally fine. Then you can just use the regular contact mode. So other uses of AFM, this brings us more to more complex nanobio realm. So you can do spectroscopy on single molecules, for example. So you can actually approach a molecule using the tip and then drag it upwards and then run some kind of Raman scattering or spectroscopy on that single molecule. So this is really state-of-the-art techniques, and you can get a signal from literally a single molecule. You can also characterize cell nucleus. You can go and do the AFM on a cell. pretty fantastic application. So AFM is also not only the imaging tool, but it's a very powerful manipulation tool, right? So you can reorganize the things in your material using AFM. So which is, really fantastic. Okay, so much for microscopy. Another method we want to cover is the X-ray diffraction. So I'm giving you definitely more information here than you need. But this is good because you will go back to this. And you can use this as a little textbook of a kind, right? So what I do with my students often, I digest information for them. So I take this 1,500-page book and I just most of the time I do things from my head. I don't even use the textbook. One of the reasons is that it's very difficult to find a good textbook these days. Why? Because nobody appreciates anymore writing the textbooks. So what is valued is just research and research only. So if you're a scientist in the West, they expect you to publish research articles, ideally in Nature or Science, and that's the only thing that matters. If you, as Professor Neogi said, he loves writing review papers, but that's considered unnecessary, and that's a very bad thing. And I think good textbooks are really badly needed, and good monographs and good good text where people just write about these general broad subjects. But you don't have that anymore. So X-ray diffraction is a technique for telling you the crystal structure. So so what you do, this is a little sketch of the crystal structure. So you have 1, 2, 3 atoms, and then again. So they're all arranged in crystal planes, and these planes are parallel to each other. And so you want to know the symmetry. You want to know the distance between these planes. You want to know the distance between atoms in a single plane. How do you do that? You do that using the diffraction effect. So you shine an X-ray light onto the sample, and then you get a diffraction. So what happens is basically the light gets diffracted from these individual scatterers, which are atoms, because they contain electrons, and they scatter X-rays. So as they basically bounce off the individual planes, you look for the satisfaction of this condition. So this condition is, when this is satisfied, you get a constructive interference of light diffracted from all the planes, one on top of the other. And so when you get that effect, you actually get a huge amplification of the signal. And that, as you see from this equation, happens only at a specific angle, theta. That angle is very important because this is how the resulting, I'll show you that here. This is how the resulting diffractograms look like. So you get peaks at specific 2 theta scale. So let's say in this case at like 32, say, degrees of 2 theta, you get a peak. And then you go back, when you get a spectrum like that, you compare that with the literature spectra, and you know what kind of crystal structure you have there. Crystal structure, really, we don't have time for that to go deeper. It requires a completely different course or multiple courses to really understand the crystallography. But you can know at least the type of arrangement of your atoms. So this is basically just giving you what is the constructive interference. You can read about that unless you already know, but you might know already. There are 2 ways you can run the diffraction. One of them is on powders, on polycrystalline sample, and the other one is on monocrystalline samples. So if you have a monocrystalline sample, such as here, what kind of X-ray do you want to use? If you have a monocrystalline sample, you need to use a polychromatic X-ray. Why? Because that way you can get the diffraction from all planes in a sample. And when you have a polycrystalline sample, all these crystals are already arranged in multiple directions, and you need to use a monochromatic light. So that is the difference. And so you know, it's useful to know, of course, because you know you can pick the right conditions. So one of them is called Laue grams. Often they look like this, and then the other one is the you know the typical powder diffraction. So you get these concentric circles, and so the distance from the center to the edge of the circle is giving you the angle 2 theta. You know, because you have a detector, and then you basically do something like this, and you know, I mean, you can calculate from here. So so in this case, the calculation is also, I mean, you know, more complex a little bit, but each of these circles is a single, you know, diffraction peak. So you have to figure out, again, to translate this into an inverse lattice. This is a really complicated process. We don't have time to cover that. But you end up with, again, with a very nice, you know, detailed characterization of the crystal structure. To me, it's always been fascinating how this resembles a starry sky, right? Doesn't it? So it's kind of a proof that this big cosmos and the cosmos inside of these little particles are very, very similar in a way, right? Because yeah.
Sir, how are nanoparticles visible to us if the wavelength of visual light is better than the size of nanoparticles?
So you use electron microscopy. So
normally, your solutions, we see the color changing.
Oh, the color's changing. The color effect, yes, the color effect, but that's a microscopic effect in a way, right? If you have a color, so the color is kind of like a, you know, a collective effect of, you know, multitude of particles. But if you want to visualize a particle as it is, you have to use electron microscope. So that is the, but yes, the color, you can see if you have particles dispersed in a solution, yeah. So the color is visible because the color is being, you know, radiated in all directions. Yes, it's a collective effect, yeah. So
it also gives a estimate of the size of the nanoparticles in that particular solution. Is it
which one? Which method?
color of the solution gives an idea of the size of the nanoparticles in that solution.
I don't think you can do that. I do not know of any method. I'm not familiar. I mean, it depends. I mean, if you know the identity of your particles, actually, you know, if you know that you have gold particles, and you know the function of the band gap with the size, right? Then you can probably do that. You know, you can technically. You know, so it probably doesn't work in general for all particles, but in that case, you probably could. But that's an empirical, right? You know, relationship. So in a way, yes. In a way, you're right. You could do that for some particles. Because right, the band gap is, if you know the dependence of the band gap as a function of the particle size. So 1225, but I'm still waiting for their reminder. I think they should remind me. Okay. So these are some of the detailed things, and you can hear about Scherrer formula. That's one of the, you know, the most important you know, equations that you will see correlated to X-ray diffraction, and extremely used by nanoparticle scientists. Why? Because you can calculate the crystallite size from these spectra. So what you see here is D, is the average crystallite size. You know the wavelength because this is a monochromatic light. So it's kind of, you know the device, you know the wavelength. Cosinus theta, you know from this to theta. So let's say you pick this peak to calculate the particle size, and you can read 2 theta. And the only thing you need to calculate is this beta. So what is beta? It's also known as the half width. So you go to a single peak, and this half width is actually the width of the peak at a half of its height. So what it tells you here is that the bigger the half width, so the broader the peak, the smaller the crystallite size. So when you have a very narrow peak, you know, kind of like a single line, you know you have a very high crystallinity. And when that diffraction peak is very kind of, you know, fluffy and plumpy like this one, you know you have a component that has a very, very low crystallite size. And the Scherrer equation works only in sub 100 nanometer range. So it's only applicable to nanomaterials. And it's extremely useful because you can know, what the crystallite size is. So that is, there are more complex things, and there are, different corollaries that I'm telling you here, but you can read more about those. Thermal energy, how does thermal energy affect? We mentioned that a little briefly. But if you have X-ray diffraction, you can really see that immediately. If this is your precipitated sample, it's highly amorphous, right? Because this peak is very broad. So the crystallinity is very low. But if you increase the temperature, which means you go up, and you get actually, the peak becomes narrower and narrower. You're right, you impart thermal energy and the crystallinity improves, and you can see that right away on the X-ray diffraction pattern. So yeah, this is just a reminder that the XRD patterns of amorphous materials are, rather diffuse. This is what the amorphous materials look like, and this is what a crystalline material looks like. So the crystallinity increases with temperature. When you have a perfectly amorphous material, you just have a noise, right? And you have that here, like a completely flat pattern, like nothing. And then once you see the peaks appearing, there's some crystallinity out there. So X-ray diffraction is a central and one of the most essential methods for characterization of materials. Ritual, we can skip that. So these are some of the frequent errors that people make using the Scherrer equation. One of them is that people often forget it's only applicable to nanomaterials, and they tend to apply them for all materials in general. They also often forget that every peak has some finite width that comes from actually the natural width. So every device has a natural width of the peak associated with that. So you can read about all these things, and then I think after the break we can cover the rest. So is that, if I'm correct, 2012, 2029, we started 2020. So I don't know, Professor Neogi is not here. I don't know what's the plan. He said lunch, but I don't know how long the lunch should be. If you want, I can keep on talking until he comes around, because I think he will be here soon. You wanna go ahead? Okay. See, let's go ahead. So these are the other methods. So the SEM is frequently coupled to EDX. EDX is known as energy dispersive X-ray analysis. So what you do here, now I'm going to mention 4 methods that are very different and yet very similar. So what you do here, I'm going to mention them one by one, and then we're going to wrap up. And I think it's very useful because I think my students find this very, very useful, this whole wrap up that I give here. Because otherwise you'll be confused by this multitude of techniques. So what happens with EDX? So you're using electrons to essentially, so look, this is an atom, and the electrons are kind of circling around them. That's a classical right view, not really true, but in a way, so what happens? You have an electron that comes, and kicks out one of the electrons from the inner orbitals. So it comes here and kicks out this blue electron, and this blue electron flies away. It's gone. And so what happens is that once it's gone, the whole atom is in a very excited state. And it has to find a way to bring itself back to a more ground state. How does it do that? It does it by one of the electrons from the outer orbitals. This red electron comes down and takes the place of the blue electron. What happens?
So why does it take out the inner electron? It's very difficult because it's closely bound. Why not the outer ones?
Yeah, it does get outer ones, but they become quickly replenished, and you don't get the X-ray signal. So this is the other part of my explanation, which comes right now. So let's say one in certain number of electrons becomes one of these inner electrons. So you're right, it becomes much harder. So, but you need only say 1 in a million or 1 in a billion of atoms to actually have this inner electron injected. Because what happens is that once this outer electron comes and takes the place of the blue electron, the energy difference between these two orbitals is radiated as actually one X-ray photon. So you calculate the difference in between the energy, the binding energy of these two atoms, and that energy is going to be equal to h n. H will be the Planck constant, and n is the frequency of that light. And then you capture that X-ray. And that X-ray is actually giving you a very unique information about what you have in your sample, right? Because you know the quantum nature of the atoms, you know, atoms are quantized. So these energies, the differences between the energies of electrons are, you know, very unique to individual atoms. So you can get an energy and you know what you have inside. So you can say we have lead, or we have aluminum, or we have silver, right? Because all these atoms are going to give you very unique X-ray photon energies. So does it make sense? So yeah, so that's how it works, and that's, you know, there's an SCM downstairs, and I just saw it, and well, not downstairs in this building, actually in the chemical engineering building, and it's coupled to EDX. So if you know this, you know how it works, right? So it's a very fundamental physical explanation, so you know where these peaks come from. Now, one of the frequent errors, and I've been really, you know, not really mad, but it's really something that the scientific community is ignoring, is that people are using EDX as a quantitative analysis. So it's been used in papers everywhere. It's been used in conferences. And what I tell everyone, you cannot use that because it's incorrect. So what they do, let's look at this spectrum here. You have, this is lead and this is copper. So what they do, and they say, okay, the ratio between the intensity of these peaks is, say, I don't know, 2 to 1. So we have twice more lead than copper. And that's wrong. That's wrong because of a multitude of reasons, and I give them here. So again, you know, I would need to spend the next 10 minutes to discuss this. So you have it there so you can read it. You know, it's kind of like more advanced, you know. And but there's a bunch of reasons why you cannot use that. And you need good calibration standards. And technically it's feasible. It's feasible, but you know, you need a bunch of preparation. So TM is also coupled to electron diffraction. So we talked about X-ray diffraction, but you can also diffract electrons, right? That's, you know, a good thing about electrons being both waves and particles, right? So you can, when you want them to act as particles, they can act as particles. They can kick out other electrons, right? And when you want them to act as waves, they can behave that way too. So you have, you can get really, you know, diffraction pattern using electrons. Transmission electron microscopy is often coupled to electron diffraction. You asked me what these patterns are, or someone else, I forgot. So these were the electron diffractions. So you see the particles here, and then you can see individual crystal planes here. See these lines, and then you take an electron diffraction pattern, and then it tells you about actually the crystal structure, you know. Because all these concentric circles, each of the circles is one crystalline plane. And if you know the planes, you know that you have, you know, atoms arranged in this or that symmetry. Now you can also do neutron diffraction. It's, you know, basically a technique that where you, so electrons, you know, are limited because you can't really get a good signal from elements that are very light. So if you want to have scattering from the nuclei, then you use neutrons. And that way you can actually figure out where lighter elements are. You know, you can even see hydrogen. So, so something that's going to be completely invisible. Basically, if you do EDX, everything with a lower atomic weight than carbon is, you know, invisible. So you can't see that. But with neutron diffraction, you can even see it. But it's you know, much more expensive and more sophisticated technique. So do we want to make a break and do the second half characterization? Or I can continue.
I think basically it's 1 hour. So can you start after lunch?
I can start anytime.
I think
just
better, isn't it? Take a pause here Then we'll again at 2 o'clock.
2 o'clock.
2
Sure.
or 2:15 maybe. It is a little bit more comfortable.
Sure, sure.
So 2:15, let's start, and then 2 hours.
2 hours.
2:15 to 3:15. Then
Yeah.
make a pause for 10 minutes, 15 minutes.
Yeah.
Then 3:30 to 4:30.
Yeah,
That will
definitely.
be perfect. That will be-
Definitely. Okay, sounds good. So, so we're going to continue then the next part
Next time.
later. Yeah.
So we'll assemble, try to come around by 2:05, just so that we can sharp start at 2:15. Or maybe 2 o'clock is possible, no? Because it is 10:30. 2 o'clock. Let's come back at 2 o'clock.
2 o'clock. Okay.
2 o'clock is better because we have 1.5 hour time.
Are we coming back to this classroom
this
or?
place, this
Okay,
place.
so I can leave this
You
here.
can
Then.
leave it here.
Yeah.
Roma, can you ask them to lock that?
I'll take my computer,
You take
but
your
I'll leave the cables.
You take your computer. Oh, then it's all good. Your phone,
Yes.
this one.
I'll apply this after lunch.
Yes, yes.
Because my back is so stiff that
Yeah.
I cannot even
Yeah,
put
it's
it
very
here,
inconvenient.
and
Hi, our lunch.
and the cable can stay here.
Exactly at 2 o'clock.
Okay.